Hi there, my name is Lana Adcock. I am a glacier tour deckhand in Whittier, Alaska. I get to work alongside glaciers every day for 6 months out of the year. So Professor Greene asked me to speak about glaciers, how they're formed, exactly what they are, what they do when they melt, how they affect the atmosphere that we live in. So I will jump right into it with the cryosphere. So the cryosphere is many different kinds of frozen water. So that could be sea ice, lake ice, frozen rivers, glaciers, ice caps, ice fields, anything like that make up the cryosphere, which cryo is the Greek word for cold. So anywhere on Earth where water exists in a solid form is a cryosphere. Although most of Earth's frozen water is found near the poles, snow and ice can be found on all 7 continents. It acts like a highly reflective blanket, and it protects the earth from getting too warm. So snow and ice reflect more sunlight than open water or bare ground, and the presence or absence of snow and ice affects heating and cooling all over the earth's surface, including the earth's entire planet's energy balance. So changes in the snow and ice affect air temperatures, sea levels, ocean currents, and storm patterns all over the world. Just as changes in the cryosphere can influence climate, changes in climate can also drastically alter Earth's snow and ice-covered areas. Unlike other substances found on Earth, snow and ice exist relatively close to their melting point and can easily change back and forth between a solid and a liquid. With just slight variations of the Earth's temperature, thousands of square miles of snow and ice can accumulate or melt, making the cryosphere one of the most powerful indicators of climate and climate change. With that, we're going to go back a few billion years. The ice ages are where the glaciers were formed, but we are technically in an ice age. So what an ice age is, ice ages began 2.4 million years ago and lasted until about 11,500 years ago. So during this time, Earth's climate repeatedly changed between very cold periods, which glaciers covered the entire Earth, large parts of the world, and very warm periods, which the glaciers melted. So the cold periods are called glacials, which is ice covering, and the warm periods are called interglacials. So scientists have recorded 5 ice ages throughout Earth's history. The Huronian, the Cryogenian, the Andean Saharan, the Karoo, and the Quaternary. And I will give these slides to Professor Greene if you guys need them. But currently we're in a warm interglacial that began 11,000 years ago. So yes, we are currently in an ice age. The last period of glaciation was about 20,000 years ago. So at that time the world on average was 10 degrees Fahrenheit cooler. That's just the core temperature of the Earth, and locally as much as 40 degrees colder. So that did affect quite a bit of the temperature. So the ice ages began 2.4 million years ago and lasted until about 11,500 years ago. During this time, the Earth's climate repeatedly changed between very cold periods, which glaciers covered large parts of the world, and very warm periods, which many of the glaciers melted. The cold periods are called glacials, ice covering, and the warm periods are called interglacials. We are currently in an interglacial ice age. So scientists have recorded 5 ice ages throughout Earth's history: the Huronian, the Cryogenian, the Andean Saharan, the Karoo, and the Quaternary ice ages. And currently we're in a warm interglacial that began 11,000 years ago, and it's the last period of glaciation, which is often informally called the Ice Age, peaked about 20,000 years ago. And at this time, the world was on an average 10 degrees Fahrenheit colder, as in the core of the Earth was colder, and locally as much as 40 degrees colder. So the temperature that you feel outside was 40 degrees colder in the current climate that you're in. So why do we know so much about glaciers? Well, Louis Agassiz was the first person to hypothesize that the Earth was once subject to an ice age. He proposed this hypothesis to the Helvetic Society in 1837 and garnered much attention. His hypothesis was as followed. Ancient glaciers had not only encroached farther south than the Alps, but in fact had reached southern Europe, Asia, North America, and led to an ice age. Several writers had expressed the opinion that these rivers of ice had once been much more extensive, and that the boulders scattered all over this region had been carried there by glaciers. So Louis Agassiz decided to make camp on top of a glacier and study this glacier, which was called Arid Glacier. And over the course of time, he wrote his most respected work, and he garnered a lot of attention for it. His final conclusion was that great sheets of ice resembling those now existing in Greenland once covered all of the countries in which unstratified gravel is found. So all of the boulders that were all over the place were being, in fact, moved by glaciers. So, what are glaciers? We should probably learn what they are exactly. Glaciers are made up of fallen snow that over many years compress into large, thickened sheets of ice. So, when snow forms in a location for an extended period of time, the weight of the snow pressurizes and turns into glacier ice. It takes 10 years to make 1 foot of glacier ice. So, what makes glaciers unique is their ability to flow. Glaciers are frozen rivers, and so they do move. Not as fast as a liquid water river, but they do, in fact, move. They can move. Generally, they average about 30 centimeters a day. They can move as much as 30 meters a day. They can measure as much as moving 2 inches a day. It just all depends on the climate of the glacier, the mass of the glacier, and how much snowfall there is. So some glaciers are as small as football fields, and others grow to be dozens or even hundreds of kilometers long. So glaciers are either retreating or advancing. It's only one of the two, and a receding glacier does not mean that the river flow is going up. A receding glacier means that it is losing more ice than it can produce. So the retreat and advance only refers to the position of the terminus, or the snout of the glacier, so what's going on at the front of the glacier. So it's like a conveyor belt. In other words, a retreating glacier does not flow uphill, it just simply melts faster than the others. So let's go over the different types of glaciers. The first one we're going to start out with is a valley glacier. It's commonly originating from the mountain glaciers or ice fields way up in the mountains, and these glaciers spill down valleys, looking a lot like a giant tongue. They can be really long, just often flowing beyond the snow line and sometimes reaching sea level. Now, this also goes into what a tidewater glacier is. So a tidewater glacier is a valley glacier that flows into the sea and calves off and breaks. So in some locations, tidewater glaciers provide breeding habitats for seals, and they're responsible for covering numerous small icebergs. So when these huge sheets of ice start to calve, they flow out into the water, and they provide a habitat for the animals that are out there looking for refuge from whales and any other kind of animal looking to find a seal for a snack. Otters also do use these icebergs for a habitat as well, though not as often as seals. We also do have a Piedmont glacier. So a Piedmont glacier occurs when steep valley glaciers spill into flat plains. So they spread out into bulb-like lobes. They don't fall into any kind of water. They just simply stop into a bowl-like area. So Malaspina Glacier in Alaska is one of the most famous examples of this glacier, and it's the largest Piedmont glacier in the world, spilling out into Seward ice field. It covers 1,500 square miles as it spills across the coastal plains. There are also hanging glaciers. So hanging glaciers form when a major valley glacier system retreats and thins. Sometimes the tributary glaciers are left in smaller valleys high above the shrunken central glacier surface. So these are called hanging glaciers. But if the entire system is melted and disappeared, the empty valleys are called hanging valleys. So why do glaciers move? So the sheer weight of a thick layer of ice causes the glaciers to flow very slowly. Now the ice is a soft material, which in comparison to rock is much more easily deformed by this relentless pressure of its own weight. So dense and heavy glacier ice begins to flow downhill. Extremely thick glaciers, which form in areas of extremely high snowfall, tend to flow faster than thinner glaciers, as their greater mass is more affected by gravity. Similarly, glaciers with steeper gradients flow faster than glaciers spread across gentler slopes. But when moving along down the mountains and valleys, they leave behind glacial striations. Now, these are scratches or gouges cut into bedrock by glacial abrasion. So the rocks and boulders that they pick up also help make these striations along the rock, but the ice is so dense and sharp that it cuts these scratches and ridges in the side of the mountains and the valleys that they go down into. And so these were first recognized as a result of moving glaciers in the 18th century when Swiss alpinists first associated them with moving glaciers. So what exactly happens when glaciers move? Well, they bring stuff with them. So till, or glacier till, is unsorted glacial sediment. So it comes from the erosion and entrainment of material by the moving ice from a glacier. So it's deposited some distance down ice to form terminal, lateral, medial, and ground moraines. So that may include clay and rocks ranging from barely larger than grains of sand to sizable boulders. Till is ultimately rearranged by rivers, leaving no organized pattern of stratification. So till is all the things that the glacier picks up and leaves at the bottom of the glacier. So what else happens when glaciers melt? Well, we're finding out that the glaciers are melting a lot quicker than they have in the thousands and millions of years before us. So scientists are finding that glaciers reveal clues about global warming. How much of our atmosphere naturally warmed up between the ice ages? How much human activity affects climate? Because glaciers are so sensitive to temperature fluctuations accompanying climate change, direct glacier observation may help answer these questions. Since the early 20th century, with few exceptions, glaciers around the world have been retreating at unprecedented rates. Some scientists attribute this massive glacial retreat to the Industrial Revolution, which began in 1760. In fact, several ice caps, glaciers, and ice shelves have disappeared altogether in this century. Many more are retreating so rapidly they may vanish within a matter of decades. So, extreme weather is also an effect of global warming. While experiencing some of the hottest summers on record, much of the United States has also been experiencing colder than normal winters. Global warming may also lead to extreme weather other than hot or cold extremes. For example, hurricane formations will change. Though this is still a subject of active scientific research, current computer models of the atmosphere indicates that hurricanes are more likely to become less frequent on a global basis, though the hurricanes that do may become more intense. So as dramatic as the retreat of one glacier may be, scientists learn most about global climate by studying many glaciers. The World Glacial Monitoring Service tracks changes in more than 100 alpine glaciers worldwide. 42 of those glaciers qualify as climate reference glaciers because the records span more than 30 years. So glacial retreat, too, is an obvious effect of global warming. Only 25 glaciers bigger than 25 acres are now found in Montana's Glacier National Park, where 150 glaciers were once found. A similar trend is seen in glacial areas worldwide. According to a study done in 2016, there's a 99% likelihood that rapid retreat is due to human-caused global warming and climate change. Some glaciers retreated up to 15 times as much as they would without global warming. So one of the primary manifestations of climate change so far is melt. North America, Europe, and Asia have seen a trend of less snow cover between 1960 and 2015, according to a 2016 research published in the journal Current Climate Change Reports. According to the National Snow and Ice Data Center, there are now 10% less permafrost, or permanently frozen ground, in the northern hemisphere than there was in the early 1900s. So the thawing of the permafrost can release landslides and other sudden landscape changes and land collapses. It can also release long-buried microbes, as in a 2016 case when a cache of buried reindeer carcasses thawed and caused an outbreak of anthrax. In 1941, Muir Glacier filled a valley in Glacier National Park and Preserve in Alaska. It was a tidewater glacier, meaning that it flowed into the ocean, but by 2004, Muir Glacier had receded so much that it was 7 miles farther back than it was in 1941 and thinned out more than 800 meters. There are also social effects of climate change, so agricultural systems will likely be dealt a crippling blow because growing seasons in some areas will expand the combined impacts of a drought, severe weather, lack of accumulated snowmelt, greater number and diversity of pests, lower groundwater tables, and loss of arable land could cause a severe crop failure and livestock shortage worldwide. The North Carolina State University also notes that carbon dioxide is affecting plant growth. Though CO2 can increase the growth of plants, the plants may become less nutritious. So, what can you do to stop climate change? Well, start with a conversation. Solving climate change requires all of us to work together, and we can't do that without finding common ground with those who don't share our perspectives. Since people often trust peers, family, and friends, and those they love, rather than scientists, experts, and environmental organizations, You can talk to people about climate change in ways that they can't. You are more likely to open people's minds with your opinions rather than those that are televised in big organizations. So if you would like to, you can learn from Climate. It's a fun and interactive chatbot that teaches you how to have conversations about climate change that decrease divisiveness and help cultivate empathy and find common ground. So overcoming polarization is key to moving forward on climate solutions. But if you want to be the most effective in changing climate change, go out and vote. Although it's important to take action in our individual carbon footprints, we need to focus on changing the larger system. That's where we have the greatest opportunity to reduce emissions. So you need to vote for leaders of all levels of government to take climate change seriously. They should commit to setting science-based targets to reduce harmful carbon emissions, implementing clear plans to watch those targets, adapting to climate change, and shifting away to clean energy. Make sure you're registered to vote, and then get informed for all elections, not just the ones that get the most media attention. Candidates' positions on climate change vary widely, so research the parties, ask questions about climate change at town hall debates, and let your candidates know you are voting for climate. Know that your vote really matters. If you're too young to vote, encourage your class or school to join a student vote program, which provides students the opportunity to experience participation in the election process. You can also talk to your parents about the importance of voting for climate action. So that's all I have on glaciers. Remember that glaciers have been around for millions of years. They've been melting for a very long time, but they are melting at a faster rate since the Industrial Revolution, and it is the human population to blame. So go out and vote and keep your Earth cold. Thanks again.